So my name is Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I drive our strategy for parallel programming models, compilers, and C++ libraries. And I've served in leadership roles for several programming languages and standards bodies, including the C++ committee, where I was the chair of the library evolution group for the past 3 years. Now happily retired from that job. It was great. I had a lot of fun, but it was a lot of work, and I'm glad that it's somebody else's problem now. So I started programming about 12 years ago, and since the start of my career, parallelism has been the focus and my passion. And I think that makes me a little bit of an unusual person, that I sort of started off programming in a parallel environment, and that's the only type of programming I've done my entire career. I have no basis for understanding programming that is not parallel, which is a little bit of inverse. Most people come into programming not from a parallel background and then have to adapt to this new and weird thing. So I had the good fortune to apprentice under Hartmut Kaiser, who taught me how to think in parallel. And I've found that the mindset that he instilled in me has been invaluable throughout the years. So by default, I think most programmers will think sequentially, and parallelism is often seen as challenging and complex. It's a tool to be used sparingly and cautiously and only by experts. But the reality is that today we live in a parallel world. Almost every hardware platform is parallel, from the smallest embedded devices to the largest supercomputers, and you must explicitly program that parallelism. So we have to change our mindsets. Anyone who writes code today must think in parallel, and parallelism must become the default. So today, we are going to focus on one fundamental parallel programming primitive upon which a lot of interesting things can be built, the scan algorithm. And through our exploration of the scan algorithm, we will cover key aspects of this parallel mindset that I think everyone must learn to develop. So a scan takes a range and a binary operator, and for each element, it produces the sum of all elements up to that element. So the scan algorithm is also sometimes called partial sum or prefix sum. In C++, we have two forms of scan: inclusive scan and exclusive scan. And we're going to only be talking about the inclusive scan today. We also have this older thing that's called partial sum in the C++ standard library. But today we're just going to be talking about what's the equivalent of std inclusive scan. So the output of a scan is a range that is of the same length as the input. And you can use any binary operator with a scan. We're going to use addition to represent the operator today. There are some requirements, though, that around the properties of that operator. Scans preserve the order of input and thus the order of summation. So therefore, the operation does not need to be commutative. So an operation like string concatenation is supported, because it's not going to change the order in which the strings would be added together. Now, to parallelize a scan, we have to introduce temporary aggregates so that we can have certain chunks of the scan be done by different threads, and then we can bind together those chunks later. And that means we need to have these temporaries. And that means that associativity and a left identity value is required to be able to do that division and grouping. So here's a simple serial implementation of scan, which operates in place. For each element after the first, we compute the sum by adding the prior element to the current element. So let's walk through the computation of a simple scan using this algorithm. So our input here will be a range of 9 single-character strings, and our operator will be string concatenation. So the first element of the result will be the first element of the input. The second element will be the concatenation of the first 2 elements. And the third will be the concatenation of the first 3 elements. And then here's what the full scan sequence would look like. Now note that the last element of the result is the sum of the entire sequence. The last element of the result is the sum of the entire sequence. This is an important property that we will rely upon later as we build out some interesting algorithms. So how do we go about parallelizing scan? At first, this may seem challenging, as the result of each element depends on the results for all prior elements. And so if you think about that, that might seem like that is a serial dependence, like you could not parallelize this. Now, when I approach a parallel problem, I tend to break it down into 3 different components. One, how will I divide and distribute the work? So today, we'll be dividing into tiles, which are contiguous subsets of the input sequence. And second, what calculations do I need to perform on each tile of work? And then third, what sort of communication needs to happen between those tiles to get me the correct final result? So of these 3, communication is the most important to identify and understand, because communication often dictates how you are going to distribute the work and what and when you should calculate. To parallelize scan, we should first consider how it communicates. And in fact, I think of scan not as a computational algorithm, but as a communication primitive. It's all about communicating information from threads to other threads. Every element of a scan sends information to all subsequent elements. The scan operator is going to see every element and propagate information from every element all the way to the end of the sequence. Ordering is preserved, which means we can reason about relations between neighboring elements. Scans can perform global, order-aware reasoning, which makes them very powerful. Now, if every element must communicate directly with every other element in parallel, then we'd have quite a big overhead. But as we've discussed earlier, we require that the scan operator we've been provided with is associative. Now, associativity can limit our need for communication because we can divide the problem up into tiles and then do a local scan of each one in serial, and then update the local scan with information communicated from other tiles to get the final results. So let's look at how that actually works. So our algorithm will take 2 inputs, a range, which will operate on in place, and the number of tiles to divide the range into. We'll launch a parallel for each on the index space of tiles. So one loop body for each tile. The body of this parallel for each is going to handle just a single unique tile. The number of tiles might exceed the number of threads that the system will use to parallelize this, which is perfectly fine. Within the tile body, the first thing we need to do is calculate the subrange of the input that this tile is going to be responsible for. And so we're going to use this range for tile helper function for this. It just divides the input among the tiles as evenly as possible and then handles remainders. So then we take all elements in each tile and we perform a local serial scan on them, which we do right here in the code. Next, we need to propagate information between the tiles. So the sum of each tile needs to be added to the elements of all preceding tiles. We need somewhere to store this information, 1 slot for each tile. So before the parallel for each loop, we're going to create a vector. And the sum of each tile is the last element of the inclusive scan that we just performed. We mentioned that earlier. So we assign that to the applicable slot in locals. Now, assignments to locals from different tiles may happen concurrently, but that is fine because each tile uses a different and unique slot in locals. And no one reads from locals yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written their sum to locals, we need to have one thread do a serial inclusive scan of locals to produce the values that need to be sent to each one of the tiles to correct all of their elements. So the result of the scan over locals will look like this. Now, the information that each tile needs to add to its elements is in the local slot for the tile directly preceding it. So next, we will go parallel again to update the elements in every tile. We're going to skip the first tile because it doesn't need any updates. There are no tiles before the first tile. And we perform the update with a serial for each, which just adds the appropriate value from locals to each element. And importantly, we add the locals value on the left-hand side. And we have to do this to preserve ordering. Even though these locals are these aggregate values that we've created that aren't actually in the sequence, we still need to preserve the overall ordering of operations to ensure commutativity. Or to ensure that we don't require commutativity, rather. So after that addition, we will have the correct result in each tile. So this is a classic, simple, and work-efficient implementation strategy for parallel scan. And by work-efficient, I mean it doesn't do any more work than you would need to. However, it requires O input temporary storage, and it has 2 passes, and thus 2 global synchronizations. So we start in parallel in the first part, the upsweep, performing the local scans and storing it into the locals vector. But then we have a global synchronization where we wait for all tiles to complete, and only then can we perform the scan of the locals vector, which a single thread does. And then finally, we go parallel again. This is the downsweep pass to perform the update of those corrected values. Now, this synchronization comes with a great cost, especially at scale. It's going to decrease the proportion of our code that can be executed in parallel and increase the amount of time that we wait with no other work to perform. So this is going to be really bad when we're moving up to larger scales. So as we scale up from a single thread to hundreds of threads on CPUs and hundreds of thousands of threads on GPUs, we're really going to feel the impacts of this. So 2 of my guiding principles in parallel programming that were taught to me by my mentor in my early years were to localize synchronization and to hide latency. So by localized synchronization, I mean that when we have to synchronize, we must minimize the set of actors that we synchronize with. So you should only synchronize with the actors that you actually have to communicate with. Oftentimes, we do global synchronization because it's easier than figuring out and setting up the actual dependencies that you need. However, while it's easier, it's also much more expensive. So if we have to wait, we want to find other useful work that we can do while we are waiting. So applying these principles to scan, we must think about what each tile actually depends upon. Does every tile need to wait for all tiles to finish before proceeding? Now, the answer, of course, is no. We only need to wait for the tiles that are preceding us to finish. So if we're in the second tile, we only have to wait for the first tile. If we're in the third tile, we only have to wait for the first and the second tile. So now we're going to implement scan a second time, and this time we're going to use a scalable strategy called decoupled lookback. So in this version, instead of a vector of temporaries, we're going to have a scan tile state object, which facilitates communication between tiles. We're going to cover how that works in detail later. We'll only have a single parallel pass this time, a parallel for each over all of the tiles. In the body of that for each, we'll compute each tile's subrange as we did before. And we'll perform a local serial scan just as we did before. But instead of storing the sum of the tile in a vector of locals, we'll pass it to the scan tile state object by calling set local prefix. And we're going to look at how that works later. Then, if we're not the first tile, we need to communicate with other tiles to get the prefix that we must prepend to all the elements of our tile. And we're going to do that by calling wait for predecessor prefix, which returns the prefix. Then we update each element in the tile by adding the prefix from our predecessors to the left. So let's break down what is actually happening here. So each tile performs its local serial scan and then calls set local prefix, which publishes the information that subsequent tiles will need. And then that tile must wait for the predecessor prefix to become available. And it does that by calling that wait for predecessor prefix function. Now, while those tiles are waiting, other tiles can begin performing their local serial scans and publishing their local results, overlapping useful work with the necessary waiting. Now, this, of course, depends upon the type of scheduler that you're using under the hood, but I'm assuming that under the hood you're using something where it can context switch out to another tile. Now, eventually, the predecessor prefixes for each tile will become available, and the tile will complete, and then another tile will start executing. So by utilizing oversubscription, that is, having many more tiles than physical threads, we can effectively hide the latency of waiting. But for all of this to work correctly, we need a guarantee that tiles are executed in monotonically increasing order. That is, tile X can only be executed if all tiles preceding X are either executing or have completed. And I call this monotonic progress. Otherwise, if we don't have this guarantee, we could stall forward progress on systems with weak progress guarantees, such as bounded thread pools or GPUs, because we could end up with a situation where all physical threads are executing tiles that are waiting for tiles that have not yet started and will never be able to start because there are no physical threads available, because they're all waiting for these tiles that haven't yet started. Now, to ensure monotonic progress, we have to change how we allocate tile IDs, or specifically how we decide which tile each iteration of this parallel for loop will work on. So thus far, we've been creating a range of integers with iota, one for each tile, and then passing that to the parallel for each. So instead, we're going to create an atomic integer, and then we're going to have each tile do a relaxed fetch add to assign a unique and monotonically increasing tile ID. And this will ensure that each loop body is working on a tile that knows that every prior tile has started executing. Now let's look at how scan tile state functions and communicates between tiles. So scan tile state contains a vector of descriptors, one for each tile. The descriptor has two prefixes for the tile: local, which stores the sum of just the elements of the tile, and complete, which stores the sum of all elements from the start of the range to the end of the tile. And by start of the range, I mean the start of the global range, not the start of that tile. A descriptor also has a state, which is either unavailable, local, indicating that the local prefix is available, or complete, indicating that the complete prefix is available. And this state is updated atomically. When you construct a scan tile state, the local and complete prefixes for each tile are just default constructed, and the state is initialized to unavailable. Now, tiles publish the sum of their elements by calling set local prefix, which takes a tile ID and a local prefix. That's the local aggregate that we're going to set. Now, the first tile is a special case. It has no predecessors, so its local prefix is also its complete prefix. So we assign the value that was passed in to both fields of the descriptor, and then we do a store release to set the state to complete, signaling that the prefixes are available. For all other tiles, we set only the local prefix. And then we signal its availability by setting the state to local. Finally, we do a notify all to wake up any tiles that are waiting on this atomic. Now, wait for predecessor prefix is called by tiles to retrieve the sum of all elements before the tile, which must be added to all of their local elements. So wait for predecessor prefix searches through the predecessor descriptors, reconstructing a predecessor prefix from the local and complete prefixes of the predecessors. So there's three different types of prefixes that we're working with here. There's the local prefixes, which are the sum of the elements in a given tile and no other elements. There's the predecessor prefix, which is the sum of all elements before a given tile, excluding the elements in the tile itself. The predecessor prefixes are what get returned from wait for predecessor prefix, and that's what needs to be added into all the elements of that tile. But they're not actually stored in the descriptor. They are just constructed on the fly. And then we have the complete prefixes, which are the sum of all the elements from the beginning of the range to the end of the tile. So a complete prefix is the sum of the predecessor prefix and the local prefix. So let's work through this in an example. That'll make it a little bit easier to understand what's going on here. So we're going to scan a vector of strings with string concatenation. So we'll divide the input into 4 tiles of 3 elements. So we start with the local serial scan of each tile, which will produce this. The local prefix for each tile is the sum of all of its elements, which is just the last element of the local scan. The predecessor prefix for each tile is the sum of all preceding elements. So for the first tile, that's nothing. For the second tile, that's the sum of the first tile, which is just ABC. For the third tile, it's the sum of the first 2 tiles, which is ABC, D, E, F. And for the fourth tile, it's the sum of the first 3 tiles, which is ABC, D, E, F, G, H, I. The complete prefix of each tile is the predecessor prefix plus the local prefix. OK, so now we understand how we compute these prefixes. Let's look at how wait for predecessor prefix actually works. So to construct the predecessor prefix, each tile will just search the descriptors of the tiles preceding it, starting at the tile directly before it, and moving backwards towards the first tile. So for each preceding tile, if its state is unavailable, then we wait. If its state is local, then we add its local prefix to the predecessor prefix, and we continue searching. And if its state is complete, then we add its complete prefix to the predecessor. And once we encounter a complete prefix in this backward search, we can stop, because a complete prefix incorporates all information from the start of the range up until the current position. So we don't need to go any further back, because somebody else has already done that work for us. So this is why we call it decoupled lookback. It's decoupled because each tile searches backwards from its position and does so independently. Independent searching is important because some threads may see the publications of prefixes before other threads, allowing them to make further progress. Now let's look at the implementation of wait for predecessor prefix. We begin by default constructing a T, which we will sum the predecessor prefix into. And next, we loop from I minus 1 to 0, going backwards. And for each preceding tile, we do a wait acquire until its state is not unavailable. If it's unavailable, we just have to wait. This establishes a synchronizes with relationship with the store releases that we saw earlier in set local prefix. So that if we see those store releases from set local prefix, we know that we can see the memory writes to the descriptor that they did. So after the wait, we're going to load the state again. And we know that the state will no longer be unavailable because states are only ever set as unavailable during initialization before the critical section. So now we know that the state is either local or complete. And if the state is local, then we add it to the predecessor prefix that we're building. And remember, we must sum it from the left to preserve order. Otherwise, if the state is complete, then we sum it into the predecessor prefix, and we stop the lookback, because the complete prefix covers all elements from 0 up until the current position, meaning that we are done. Now, once we finish building the predecessor prefix, we must compute and publish our own complete prefix. So we compute it by just summing the predecessor prefix with the local prefix. And then we signal its availability with a store require of complete to our state and a notify to wake up anyone waiting on our state. And this synchronizes with the wait earlier in this function, ensuring that if a thread observes the state is complete, they will also see the write of the complete prefix. And then finally, we return the predecessor prefix. So again, let's work through an example to understand how this actually operates. So here's a snapshot of a scan execution with 8 different tiles. So let's perform wait for predecessor prefix for tile 3 here. So we start by looking at tile 2, whose state is local. We sum its local prefix into our predecessor prefix. Next, we look at tile 1, whose state is local. Notice that tile 1 has written its complete prefix. We see it here in the table. But we haven't observed the state change yet, so we can't use it. We haven't seen that atomic write yet, even though we might be able to see that in memory. Instead, we sum its local prefix into our predecessor prefix. Finally, we look at tile 0, whose state is complete. And so we can add its complete prefix to our predecessor prefix and finish. Next, we compute our complete prefix by summing the predecessor prefix and our local prefix. And we write it to our descriptor and set our state to complete. So next, let's walk through what we would do for tile number 5. So we start at tile 4, whose state is local. We sum its local prefix into our predecessor prefix. And then we look at tile 3, whose state is complete. So we sum its complete prefix into our predecessor prefix, and then we finish. We get to stop early here because we found a complete prefix. We don't need to go back and duplicate any work that it's already done. Finally, we calculate our complete prefix, and we store it to our descriptor and update our state to complete. And that's it for scan tile state. And so now we should have an understanding of how we perform communication in this decoupled lookback scan. So our decoupled lookback implementation needs only O tiles storage, while our 2-pass implementation that we saw earlier needed O input storage. Now, for context, for the benchmarks that I ran with 4 billion elements and 1,000 tiles. So you'd much rather need only order of 1,000 tiles temporary storage instead of order of 4 billion input elements temporary storage. So our decoupled lookback implementation is a single pass, which means it only needs 1 global synchronization, while our 2-pass approach needed 2 global synchronizations, the one internally and then the one at the end. So running some benchmarks of this, I observed this decoupled lookback scan perform about 3 times faster than the 2-pass scan on a 64-core CPU system with a 4 GB problem size. Now at GPU and distributed scale, decoupled lookback will outpace the 2-pass approach even more. Now, as I said at the start of this talk, Yeah, Tristan?
Is this performing more work than is strictly necessary?
Is this performing more work than is strictly necessary? Yes. As I said, the two-pass approach was a work-efficient implementation. This is not work-efficient. This might duplicate work.
So if your scan operation is particularly expensive, would the dynamics of this change?
If your scan operation was particularly expensive, would the dynamics of this change? It might. Yes. You are never duplicating an entire tile worth of work. You're duplicating aggregate calculations here. So the work complexity of the duplicated work will be in the O tile regime. So typically the order of magnitude of tiles that you're going to pick is going to depend on the type of execution resource that you're using. But usually, like on GPUs, that might be a few thousands to tens of thousands. On CPUs, it might be hundreds to thousands. But that's usually not going to be enough that even with an expensive operator that you're going to notice it. If you have 4 billion input elements and you were duplicating an expensive scan operation order of magnitude 4 billion times, you'd notice it. If you're duplicating an expensive scan operation a few thousand times, when you're doing 4 billion of the scan operators, you're not going to notice that. But certainly, if the order of magnitude of tiles is closer to the order of magnitude of the problem size, you'd notice it. But there's not really any hardware that looks like that. Good question. So as I said at the start, scan is worthy on its own, but its importance lies in what we build with it. Many problems have a summing, counting, filtering, searching, or neighbor-aware aspect that can be solved with a scan. And so we're going to look at two different examples today. The first one is copy-if. So copy-if takes an input range and a unary filter operation. So as an example, here we've got a range of characters and a function that returns true for the characters that are letters. So it produces a range that contains only the elements of the input for which the filter operation is true. So copy-if cannot be evaluated for each element in isolation. To determine the correct place in the output to write an element, we must know how many elements before this one will pass the filter. And that is a counting task that needs to be done for each element, and that sounds like a scan to me. So we're going to start off with a simple implementation. Our copy-if function will take an input range, an output iterator, and a filter operation. So first, we create a vector with a flag for every input element. Then, in parallel, we will evaluate the filter operation for every input element, storing the result in the flags vector. Next, we're going to do a scan of this flags vector with integer addition as the operation and integers as the output. This is called a plus scan. We'll create storage for the output of our plus scan. That's going to be another vector. We need one integer for each element plus an additional integer for the final count of how many elements we've copied. And just trust me on that for now. That'll become clearer in a moment. So next, we do a parallel scan of flags into indices, starting at the second element of indices. The first element of indices has been default initialized to 0, which is always the correct output index for the first element that we're going to output. Now we write into the indices vector offset by 1, and let's look at an example to understand why. So let's build the indices vector for this example problem we saw a moment ago. By fiat, as I said, index 0 is always 0. That's just how we initialize it. And we offset the output by 1 because when we encounter an element that is true, we output it at the current index, and then we bump the index for the next element that we write. So A here is a letter, and it's going to be written at index 0. And so that means that the next letter will be written at 1, so the second element of indices is 1. B is also a letter, and will be written at index 1. So the next letter will be written at index 2. Now 2 is not a letter, so it will not be written, and thus the index is not incremented. Likewise, 3 is not a letter, and the index is not increased. The same is true for 4. And then E is a letter, and so it will be written at index 2. And then the rest of the indices are scanned in a similar fashion, which will produce this. Now we perform the next step where we walk through the flags vector, and for every true flag, we write that element at its associated index, and we call this the write pass. So A is written at index 0. B is written at index 1. E is written at index 2. G is written at index 3. And the final element of indices has the count of how many elements were written, 4. Now in this case here, the last element happened to be false, but if it was true, then we would have 4 and then 5. And so that's why we need to have that last element there to keep the count of how many we've actually written. So let's look at the write pass in code. It's a parallel for loop that iterates the input, flags, and indices. So we'll just zip them together. For each element, if the flag is true, then we write the element at the associated index. To calculate the bounds of the subrange that we've produced, we use the last element of indices, which will give us the count of how many elements were written. And then we use stood ranges, subrange to construct the range that we need to return. And with that, we have a parallel copy-if implementation. Now, this implementation needs a lot of temporary storage. It's on the order of magnitude of twice the size of the input. It also uses 3 different parallel passes, which means we have 3 global synchronizations, 2 of which we would hope to avoid. So we've got this stood vector of flags, we got this stood vector of indices, both of which are order of magnitude the size of the input, and we've got 3 whole synchronizations. So this is not great. So now we can improve this with decoupled lookback. So now we need to take a tile size in addition to our other parameters, as we're going to be doing tiling, which we weren't doing in the prior example. So we need a scan tile state for indices and an atomic to assign tile IDs, just as we saw in the implementation of scan itself. Next, we've got our tile loop. And in the body of the loop, we assign the tile ID and calculate this tile's subrange, just as we did in the inclusive scan decoupled lookback implementation. And next, we'll create tile local storage for flags, 1 for each element in the tile, and evaluate the filter operation into the flags. Now, we're dynamically allocating this storage on the fly here, but it could also be pre-allocated depending on how many physical threads we have. Or it could be statically sized on the stack, which would require static tile sizes, and that's how we do it on the GPU. Now, we do end up, at the end of the day, creating the same amount of temporary storage here. The difference is in the lifetime. You only need as much temporary storage as you have physical threads that will be active, instead of needing to allocate the temporary storage for the entire thing at once. Then we'll create tile local storage for the indices as well. And then we'll perform a decoupled lookback scan of flags into indices using set local prefix and wait for predecessor prefix, just as we did in inclusive scan. So we'll output into indices offset by 1, just as we did in the 3-pass copy-if implementation that we just saw. And then finally, we'll do the write pass. And then we will return the subrange of elements that we output using the last tile's complete prefix, which will have the final count of the elements written. So now we have a much better copy-if implementation. It only needs O tiles storage instead of O input storage. So remember, in my testing, I was using billions of input elements and thousands of tiles. So on the system I was benchmarking this on, I observed the decoupled lookback copy-if perform about 11 times faster than the 3-pass copy-if. And that was a 64-core CPU system with a 4 GB problem size. So now let's move on to the climax of this talk, an algorithm that I think is really quite beautiful, which is chunk by. So chunk by takes a range and a binary comparison operation. It's going to split the input range into subranges in between each pair of adjacent elements for which the comparison operation returns false. So its output is a range of subranges. So in the example shown here, we have text with new lines and an operation that returns true if the left-hand side is not a new line character. So this will split the text into individual lines, each one terminated with a new line. Now let's look at another example. We've got a range of 9 characters and the equality operation as our chunking operator. So for the first 2 adjacent elements, this operation returns false. And then for the next 2, it's true, and then false, indicating the end of a chunk. Then true, then false. Again, we're at the end of a chunk here, and so on. And we can see from this that we have 4 different splits, that's the 4 falses, and 5 different chunks that we need to form. The A chunks, the G chunks, the C chunks, the T chunks, and then the second A chunk. So how do we go about parallelizing this? So there's 3 pieces of information that we'll need to communicate. Again, we want to think about communication here. So first, we need to know what index is this chunk in the output. How many chunks came before it? This is very similar to copyif, so we're going to do similar things to what we did in copyif. Next, we need to know where each chunk starts. And finally, we need to know where each chunk ends. So we're going to define a data type that will track all this information for each element. And we're going to call it interval for reasons that will become apparent. So an interval has 4 members. It has a flag, which has the result of applying the comparison operation. So it is false if there is a split between this element and its neighbor to the left. And it is true otherwise. An index, which indicates the current group, which should be written in the output, is the next member. And so this is going to be a plus scan of the inverse of flags. So both flags and index are calculated in a similar fashion to what we did in copyif. And then we have a count, which keeps track of how many elements share an index with this element. So all elements that share an index are going to be in the same chunk. And finally, we have end, which is simply a running count of how many elements we have in total. And this gives us the position of the current element. Next, we need to define how we sum intervals. And this is like the complicated part, the magic behind this algorithm. Think of an interval as an aggregate of 3 different summed components: the index, the count, and end. Its sum operation, therefore, must perform 3 separate but related sums. We don't sum flags. They are set by the comparison during initialization of the range of intervals. So flags will already be set at the time that the sum operator is going to run. So when adding 2 intervals, we always take the flag from the right. Index is initialized to the inverse of flags, and then we just plus scan it. And it's the inverse of flags because a false in flags indicates the end of a chunk. And so what we want index to be is that we want it to count, basically how many chunks we have. Now count is a little bit trickier. It tracks how many elements are in the current chunk. And so it needs to be reset whenever the current chunk ends. And we can tell that the current chunk ends when the index changes. And the index is going to change when the right-hand side flag, or when the index on the right-hand side is non-zero. which indicates that we're at the end. Then finally, for end, we just do a plus scan. So end will be initialized to 1 for every element and to 0 for identity objects. Now, suspend disbelief for now. We're going to work through an example that will demonstrate how all of this actually operates. So our chunk by algorithm takes an input range, an output range, and a comparison operation. And we're going to start off by writing a simple multipass version. So we'll need a vector of intervals, 1 for each element, plus an additional 1 for the final count of how many chunks we have. And this is similar to what we need for copyIf, just with intervals instead of indices. And next, we need to initialize the intervals. And we're going to start off by initializing the interior points of the intervals, so everything except the first and last elements. And we're going to do this initialization in parallel. For each interval, we have to look at 2 adjacent elements, as our comparison operation must be applied to every 2 elements. So an interval always represents the element on the right-hand side of the operation. We also need a special identity value on the left to handle the first element, and a special identity value on the right to close the last group and give us the final count of how many chunks we have. We're going to handle the identity values here, before and after the initialization of the interior points. For each interior point, we first evaluate the comparison operation. We set the flag to the result of that comparison, and then we set the index to the inverse of that, because we're going to plus scan it, as we said earlier. We're going to do a plus scan of the inverse of flags. Then we initialize both count and end to 1, as this interval at this point in time represents a single element at this point. And so the count of how many elements are there is 1, and the end index would be 1. So for our example problem, the initial state for the interior points will look like this. For the first element, the left identity, we set flag to true because it does not represent the end of a group. We set index to 0 because that's the index that we'll start writing to in the output. For the right identity, the last element, we need to end the last group. So we need it to be a new group indicating that the last group is done so that we have the correct count of how many groups we're going to have. So we set flag to false, which indicates a split, an end of a group. And then we set index to 1, which indicates that this element does not belong to the same index as the prior element, or the same chunk as the prior element. So with the addition of those special identity values, we have our completed initial state for intervals for this example problem we've been looking at. So next, we do a parallel scan of intervals. Let's walk through that for our example problem. So first, we're going to handle index. So we just plus scan index, which starts off as the inverse of flags. And so we end up with this. It's quite similar to what the scan for copyIf looks like. Next, we scan count. And remember, count gets reset whenever the index changes, or whenever we start a new chunk. So for the first element, the output is the same as the input, 1. For the next element, the count gets reset because the index has changed. We're on a new group. So the index on the left is 1, and the index on the right, or the index on the left is 0, the index on the right is 1. And then for the next element, the count increases because the indices are the same. So we've got another element that's been added to this chunk, and that's what we're counting here, how many elements are in the current chunk. And for the next element, we've reached the end of a chunk, and so we once again reset the count. The indices are equal for the next element, so the count is increased. We're adding another element to this chunk. Likewise for the element after that. And then we proceed in this fashion for the rest of the elements, producing this. Finally, we need to handle the scan of end, which is a bit simpler. This is just a plus scan with no reset. And every one of these has been initialized to 1. So we end up with this. And this is what we're going to have in our intervals vector after our scan. So next, we have the write pass, where we're going to use this information that we've built up in intervals to produce the chunks. The write pass is done on the adjacent intervals, which is different from what we did for scan and copyIf, where we just performed it on the scanned indices. Here we're working on adjacent pairs of these intervals that we just constructed. If the flag on the right interval is false, then it represents the end of a chunk. The right interval represents 1 past the end of the chunk. The last element in the chunk is represented by the interval on the left. So that interval on the left is what we're going to use for the write. And we write to the index specified by the left interval. And we write a subrange, which is constructing the indices of the beginning and the ending using the intervals end and count members. Range indices are half-closed in C++, so the ending should be the indexed 1 past the end of the last element, which is what end is. So interval.count has the count of the elements in this chunk, and end has the index 1 past the end of the current element. So the index 1 past the end of the subrange is just the interval's end member. And in the beginning of the interval is the index 1 past the end, which is interval.end, minus the count of the elements in this chunk, which is interval.count. So we just do end minus count to get the start. So here's what the constructed subranges look like for our example problem. We have 4 splits here producing 5 chunks. We have 5 false flags, 4 from the splits, and then 1 from that special write identity element. So the first chunk starts at 0 and ends at 1 with a length of 1. The second chunk starts at 1 and ends at 3 with a length of 2. And you can see we compute the start of this one by taking 3 minus the count, 2, to get 1. The third chunk starts at 3 and ends at 6 with a length of 3. And again, you can see we compute the start of this chunk by taking end, which is 6, minus the count, which is 3, how many things were there, and then that gives us the start. And the fourth chunk starts at 6 and ends at 7 with a length of 1. And the fifth and final chunk starts at 7 and ends at 9 with a length of 2. And then finally, we return a subrange of all the chunks that we wrote. And we get the count of how many chunks we have from the last interval index, similar to what we did for copyIf. And that comes from that magical write identity element. In the case of our example problem here, it is 5. You can see highlighted in orange, the index for that last element is 5, and that's how many chunks we have. And that's it. We have our chunk by algorithm. And as with copyIf, this requires O input temporary storage and has 3 global synchronizations, which is not ideal. So let's rewrite this with decoupled lookback, just as we did for copyIf earlier. So again, we'll be taking an additional tile parameter now, as we're going to be tiling here, as we weren't in the simpler version. We'll create a scan tile state of intervals and an atomic to assign tile IDs. As with all our other decoupled lookback algorithms, we'll have a single parallel for each over the space of all the tiles. And each tile will determine its tile ID via that atomic. Because many of our calculations here are performed on adjacent views of ranges, and we must add the special identities values on the left and right, we must treat the first, last, and interior tiles differently in a few different places. So we'll define 3 bools to classify what kind of tile we have: first, last, or interior. We define them right here. And then next, we'll calculate the subrange of elements that belong to this tile. So for the first tile, we'll skip the first element, which has no neighbor to the left. Recall that we did this in the multi-pass version by offsetting the output of our scan by 1. Next, we must initialize the intervals, just as we did in the multi-pass version, except this time we do it locally in serial within each tile. For the interior tiles, we need 1 less interval than we needed for the first and last tile, because the first and last one have those special identity elements. This is, and we're going to assign those first and last identity elements right here. And they're initialized only if we are in the applicable tile that has an additional slot for them, which is the first one and the last one. Next, we initialize the interior points. For the first tile, we start off by 1 to skip over the left identity. And the initialization of the interior points is done just as it was in the multi-pass version. Next, we perform a decoupled lookback scan of intervals with a local serial scan, set local prefix, and wait for predecessor prefix, and an update pass, just as we've seen in all the other decoupled lookback examples. And then finally, we have the write pass over adjacent intervals, which looks very similar to what we had in the multi-pass version that we just saw. And so if the flag on the right interval is false, then we write out the chunk using the information from the left interval. Again, just as we did before. And then finally, we return the subrange of all the chunks, which is this range of ranges. And we use the complete index of the last tile to get the count of how many groups we wrote out. And that's all there is to it: a parallel and scalable single-pass chunk-by algorithm. And so this only needs O tiles storage and a single global synchronization. In my testing, it performed about 9 times faster than the 3-pass implementation on a 64-core CPU. So these are just a couple examples of what we can build with scan and decoupled lookback mechanisms. Scans and decoupled lookback can be used to solve all sorts of problems. Anytime you're doing summing, counting, filtering, searching, sorting, things like that, they tend to be a good fit for the scan. And in the cases where scan isn't a good fit, it's usually some form of a reduction when you're solving it in parallel for any of those types of tasks. So there's kind of 3 key principles that I hope you'll take away from today's talk. The first is focus on communication, because it dictates almost everything else about the design of a parallel algorithm. Localize synchronization and avoid global barriers, because they reduce scalability and performance. And overlap weighting with useful work wherever possible so that you can hide latency. And if you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast, ADSP, Algorithms plus Data Structures equals Programs. It's available on all streaming platforms. Go subscribe now. We'll probably record an episode here at the conference. So if you want to be on the podcast, come find us when we're walking around with a microphone. And I want to thank Connor, who contributed greatly to the development of this talk, and also my colleague David Adelstein, who's here in the audience, who the first time I gave this talk, I sent him the slide deck 10 hours before the talk and asked him to review it, and he sent back extensive notes in those 10 hours, which I thought was quite impressive, and I was able to incorporate most of them into this talk. And I also want to thank Dwayne Merrill, Jared Hubrecht, and Michael Garland, whose groundbreaking research on parallel scans made this talk possible. And thank you all for your attention, and I hope to see you all at next year's conference. And saw we had a question there.
Yeah, great talk. Thank you. Thanks a lot. Okay. So first, basically you showed us these 3 types of optimizations that I think are sometimes called loop fusions in the serial world.
Yeah.
It's sort of like the compiler's purview.
Yeah. It's hard in C++ to do this as a compiler optimization. In something like a higher level, like functional language, you could certainly fuse these things together. And we have some conversations about, oh, could you define an algorithm's MLIR dialect to do this sort of thing? You essentially, to be able to do fusion of these sorts of things, you'd have to have a language where you've got some first-class notion of arrays or inputs and some first-class notion of the underlying algorithmic operations, because the compiler has to be able to see, like, oh, like you've got this followed by this, like I can merge it together. But the reality is that in most of these languages, I mean, maybe something like chunk by is the example here, where you would maybe not have a built-in chunk by operation and you'd want to define it in terms of like scans. But like I would imagine most of those languages would have a thing like a copyif built in, because it's a fairly fundamental thing. But yeah, you can certainly, in the right type of language, you could do these sorts of things via fusion. Other questions? Sure.
Thanks a lot again. So you mentioned the memory of these optimized things being all of tiles. What is tiles? Like, is tiles the number of tiles or the size of memory?
It's the number of tiles. So like the example of let's see. If we go back to wherever scan tile state is defined, which will take a little while. But if you look at like,
Go forward to, or maybe slide 142, I think.
Well, let's go back to scan tile state, and I'll explain where we'd find it. So like you're going to have one of these things for every tile, and each one of these things has like, this has like O of 1 storage. It doesn't have any in thing. The one place where I cheat is in the cases where you need tile local storage. You need a little bit, it's still order of magnitude of tiles, but it's also to some degree a function of the input size. So you need like however many tiles times like the size of each tile temporary storage. Which is still going to be, in a case where you have orders of magnitude more input elements than you do tiles, and where that means you're going to have a small, because the tile size is a function of how many tiles you have and the input size. So it just by definition will be smaller. And in fact, I think that actually O tiles may be the right regime even for the cases where you have the tile local storage, because of what I just mentioned there, where the tile size is a function of the input size and how many tiles you have. So like the actual computation of how much temporary storage do you need when you need the local scratch space, it's going to be like tiles times tile size, but tile size will be equal to like input size divided by tiles. So then you've got a function there where you've got tiles times input size divided by tiles. Yep. All right. Any other questions? Or yeah, I'll take one more.
There is kind of an approach which is similar to what you were doing, but it's also optimized for submission. Like, have you seen how like TBB does sort? Basically, very similar to this, but they have tasks submitting other tasks, and that optimize the load on the submission queue on the scheduler.
Yeah.
So have you considered doing something like this, and would it?
Yeah, this comes up every time we do the talk. That instead, like in the scan approach, instead of like relying upon schedule or load balancing, you could submit the upsweep at the local prefix scan as a task, and then you could like chain a continuation onto it, and like you could set up like a task tree. Yeah, you could do that. I write this the cooperative way because I'm like used to the GPU environment. So yeah, like you could do this in the task style. It would make maybe more sense for CPUs. It would allow you to hide your latency a bit better. Yeah. Like essentially any place where there was like an atomic wait or like a separate phase of computation. You could instead just have that be like a task that you launch. Yeah. All right, I'll be around if people have questions. Come find me.